Welcome to this first set of lectures on the science of hydrology, where I'll focus mainly on the historical development of the science, but will also briefly address its future perspectives, a future you will play a part in as a participant in the Master of Science program at IHE Delft. I'm Michael McClain, one of the professors at the Institute. I'm an eco-hydrologist, which means my work focuses on the interactions of the hydrological cycle and ecosystems. Eco-hydrology is one of several subdisciplines of hydrology where the science links to neighboring disciplines, such as geology, chemistry, biology, ecology, and the social sciences. But more about that later. Let's begin with a basic definition of hydrology itself. Hydrology is the science that deals with the processes governing the depletion and replenishment of the water resources of the land areas of the earth, and treats the various phases of the hydrological cycle. This definition comes from a 2019 paper by Rosbjerg and Rhoda, and it captures well the two fundamental aspects of hydrology. First, that it's a geophysical or earth science focused on the natural occurrence and movement of water on, above, and below the land areas of the planet. Water occurs in the atmosphere, in rivers, lakes, and aquifers, in glaciers and snowpack, as moisture in the soil, and in the bodies of plants and animals. And it cycles between these mainly through processes of evaporation, evapotranspiration, precipitation, infiltration, and runoff. In so doing, it plays essential chemical and physical roles shaping the surface of the land, supporting life and regulating the energy balance of the planet. It's a substance like no other, and it's irreplaceable. Water is, of course, important to the lives of all people and to our socioeconomic well-being, which brings us to the second aspect of the definition of hydrology, which is that it's the basis for water management and hydraulic engineering. The definition refers to the depletion and replenishment of water resources, which are needed for drinking and sanitation, for growing food, generating power, use in our industries, and for sustaining aquatic ecosystems. Water resources may also threaten our health and safety when polluted or in times of drought or flood. The science of hydrology focuses on the processes influencing the availability of water resources at spatial and temporal scales relevant to water management. This includes monitoring the availability and quality of water through time and forecasting it into the future. The growing influence of human activities has led to revision of the natural water cycle I showed in the first slide to now include human influences. This represents a more accurate depiction of the global hydrological cycle today, and the science of hydrology now focuses on this coupled human and natural system. I'll pause the lecture here so you can examine this diagram in more detail. Note that human-dominated hydrological flows are indicated by the blue, green, and pink arrows. Blue arrows depict flows diverted to or from rivers, lakes, and aquifers, while green arrows depict flows through human-controlled vegetation like crops and managed forests. Pink arrows depict flows of wastewaters that often carry with them contaminants that degrade water quality. Now let's leave the present and return to a time when human influences on the hydrological cycle were far less. Because of the fundamental importance of water, ancient human societies worldwide developed in-depth indigenous knowledge of water availability and its seasonal and even interannual variations. This was especially true for societies in arid and semi-arid climate zones. We know from archaeological sites in the Middle East, Northern Africa, and Asia that as early as 5,000 years ago, civilizations were constructing structures to store and transport water. References to the processes influencing water availability appear in early religious texts, recognizing aspects of the hydrological cycle. But the explanations for these processes were generally attributed to supernatural or divine forces. These are images of structures constructed by the Nabateans approximately 2,500 years ago in what is now the country of Jordan. The earliest written evidence we have of a natural philosophy of hydrology, separate from mythology, comes from the ancient Greek philosophers, who recognized nearly all components of the hydrological cycle, including lakes, rivers, wetlands, and subterranean waters, and the processes of evaporation, condensation, precipitation, infiltration, exfiltration in springs, and runoff in rivers. But they disagreed and debated among themselves on the exact nature of the components and how they were interconnected in the hydrological cycle. Early process observations similar to those of the Greeks may have been made in other parts of the world, but it's from these ancient Greek origins that we can trace the history of current hydrologic science taught at IHE Delft. Aristotle's views were to have the most long-lasting influence. More than 2,300 years ago, in his treatise Meteorology, Aristotle described the nature of air and water on the earth. His explanations of the processes were of course quite different from those of today, but he understood that water cycles through the Earth's system and that evaporation of seawater is a source of fresh water falling as rain. However, unlike some of his predecessors, he did not believe rainfall was the main source of water flowing in rivers. It was thought that there was too little rain to account for the volume of river flow, and that rain simply evaporated back into the atmosphere. He believed the water flowing in rivers derived from the continuous condensation of water droplets in interior caverns of mountains, and as the quote on the screen says, the water at first trickles together little by little, and the sources of the rivers drip, as it were, out of the earth, and then unite. Now let's fast forward through the Middle Ages when natural philosophy languished, to the Renaissance period when science began to flourish and polymaths of the time like Leonardo da Vinci began to test and refine the ideas of the ancient Greeks. Da Vinci was fascinated by the movement and cycling of water and by its physical characteristics as a gas, stagnant or flowing liquid, ice, and snow. He was also a problem solver and concerned about the hazards of floods and how they might be mitigated. He began conducting experiments to investigate the occurrence and movements of water, designing instruments to measure and quantify the phenomena he observed. He also wondered about the origin of rain and water flowing in rivers. He agreed with Aristotle that rainfall could not be the source of water flowing in rivers, but he believed the source must be underground conduits linked to the ocean. He hypothesized that subterranean water was lifted to springs in the mountains by capillary forces, or forces similar to those operating in a siphon. Da Vinci's writings on hydrological processes were never formally published, but they've been widely cited in the hydrology literature. The book by Pfister and others cited on the slide also provides a fascinating account of his work, a convincing argument that, while his theories of the hydrological cycle were incorrect, the approach applied by Da Vinci marks the beginning of scientific hydrology. In this European history, Bernard Palissy is credited with first publishing that rain is the primary source of water flowing in springs and rivers. Palissy published his arguments in 1580, just 60 years after the death of Da Vinci. But unlike Da Vinci, Palissy did not arrive at his conclusions through experimentation or measurements, but based purely on his observations and inductive reasoning. He described that rain falling on mountains and upstream lands required time to reach springs and rivers, implying infiltration and movement as groundwater. He said, quote, "All springs are fed from the end of one winter to the next," end quote, meaning one rainy season to the next. Looking back from today, we see that his general arguments were spot on, but they had little effect in changing the minds of his contemporaries. By this time, the scientific revolution was in full force in Europe, and new theories on natural phenomena were expected to be supported by quantitative data and analysis. It would be another 200 years before scientists were able to sufficiently quantify and link precipitation runoff and evaporation, expressing the hydrological cycle more or less as we understand it today. 4 individuals are usually credited with this. The first was Pierre Perrault, who made simple rainfall measurements and calculated that the volume of rain in a subcatchment of the Seine River was more than sufficient to account for the volume of flow in the river. He published his work anonymously in 1674 in the book L'Origine des Fontaines, or The Origin of Springs. This was certainly a breakthrough, quantitatively supporting the earlier observations of Bernard Palissy. But Perrault failed to understand that rain infiltrated into soils and fed springs and rivers via groundwater flows. Scientific explanations of that critical component of the cycle were added a decade later by Edmé Mariotte, who recognized the importance of infiltration along preferential flow paths, and he also improved on Perrot's quantification of rainfall versus runoff in the Seine basin. The case was now made for precipitation being sufficient to support runoff. Next came the work of Edmund Halley, who conducted experiments on evaporation and showed quantitatively that the amount of evaporation from the Mediterranean Sea was sufficient to account for the flow of rivers discharging into it. Halley recognized that evaporated water condensed to form precipitation, and that precipitation contributed to the flow of rivers. But strangely, he also adhered to the Aristotelian view that a significant amount of water vapor penetrated into the interior of mountains, where it condensed to form springs. So while the theory was still a bit flawed, a quantification of evaporation had been added to the equation. But it was not until the work of John Dalton that the cycle was finally closed in a convincingly quantitative way, and the theory of massive subterranean water condensation was finally put to rest. By this time, rain records were available for at least 30 gauging stations across England and Wales, and Dalton conducted multiple experiments of his own to quantify evaporation and how it varied with temperature and atmospheric pressure. He used the available rainfall data, his own analyses of evaporation, and estimations of runoff drawn from the work of others to construct the regional water balance. He hypothesized that if rainfall was the main source of both river runoff and evaporation, then the amount of rainfall should equal the sum of the two. His numbers balanced within 20%, which he found satisfactory, accounting for the uncertainty in the measurements and recognized unknowns such as changes in storage. So, more than 2,000 years after the hydrological observations of the ancient Greeks and 300 years since the initial hydrologic measurements and experimentation of Leonardo da Vinci, the essential elements of the modern hydrological cycle and water balance equation were now established, and the science of hydrology was poised to enter a period of rapid advancement. We'll look at that period in the next lecture.